Hello, and welcome to this intermediate webinar series on disaster assessment using synthetic aperture radar. I'm Dr. Erika Podest, and I am a scientist in the Earth Science Division at NASA's Jet Propulsion Laboratory, located in Pasadena, California. I'm very excited about this webinar series. It contains 3 sessions. Today's session is focused on SAR for flood mapping, and we have 2 amazing guest lecturers covering the following 2 sessions. Dr. Erika Fielding from NASA's Jet Propulsion Laboratory will teach the second session, which will be on landslides. Dr. Malene Johansson from UiT, the Arctic University of Norway, will teach the third session, which will be on oil spills. Each session will cover theory and a hands-on demo. Today, I will begin with SAR theory as related to flooding, and I will then go through a demo on how to generate a flood time series product using Google Earth Engine. Each webinar or each session in this webinar series will be in both English and Spanish on the same day, and the presentations and the recordings will be posted online in a couple of days, and they'll be posted on the ARSET page for this webinar. So as mentioned, there will be 3 sessions, and each session will be up to 2 hours long, and that includes the presentations, the demonstration, and the question and answer period at the end. The same content will be presented at 2 different times each day. So session A will be presented in English, and session B will be presented in Spanish at the times that you see here on the slide. All materials and recordings from each session will be available through the ARSET training page for this webinar, and that can be accessed through the link that you see on this slide. There will be 1 homework assignment for all 3 parts of the training. And the homework will be in a Google form format, and answers must be submitted via that Google form. And that homework can be accessed from the training page, the ARSET training page for this webinar. The homework will be made available on the last session, so that's October 27th, with a due date of November 17th. A certificate of completion will be awarded to those who attend all live webinars and complete the homework assignment by the deadline. You will receive a certificate approximately 2 months after the completion of the course from Marinés Martins. So these are the prerequisites. We're hoping that you've had the chance to refresh your memory on the basics of SAR and INSAR, as well as the sessions that covered the use of SAR for floods and landslides. So we'll be building on that. And we'll also be introducing a new topic, which are oil spills. And so we will be providing some refresher material in the presentations in case you weren't able to go back and review this previous material. So this is the training outline. As mentioned, today I will be talking about SAR for flood mapping. Tomorrow, Thursday, October 20th, Dr. Erika Fielding from JPL will be talking about SAR for mapping landslides. And then next Thursday, October 27th, Dr. Malene Johansson from the Arctic University of Norway will be talking about SAR, the use of SAR for oil spill detection. Learning objectives. By the end of the session, attendees will be able to understand the information content in SAR images relevant to flooding, understand the confounding factors in SAR relevant to flooding, access, process, and visually interpret SAR data, and generate a time series flood map using Google Earth Engine. In terms of what's going to be covered, here we have the outline. I will first go through a radar overview, discussing this radar signal interaction with the land surface, radar and surface parameters, distortions in the radar images, confounding factors when looking at flooding, and available SAR data. And then we'll go into the demo, and we'll be using time series data from Sentinel-1. We will first define an area and time period of interest. We'll visualize the SAR data, and then we'll be generating time series flood maps with the data. Let's start with a radar overview. If you're already familiar with this material, then hopefully it will serve as a refresher. Let's start with the electromagnetic spectrum, and that's the range of electromagnetic energy that spans from very long wavelengths to very short wavelengths. Most remote sensing sensors are designed to operate at specific regions of the electromagnetic spectrum according to the objectives they intend to achieve. Microwave sensors operate within the range delineated in this figure, which is at a much lower frequency or longer wavelength range than optical and infrared sensors. So, to put things into context, the wavelength of light is about 390 to 700 nanometers, while for microwaves, it's on the order of 0.3 to 100 centimeters. And because of this huge disparity in wavelengths, the features on the Earth's surface appear differently in the microwave range than in the optical range. So the information content in SAR images is different than the information content in optical images. So, of course, there are advantages and disadvantages of microwave remote sensing over optical. And some of the advantages, as you all probably know, is that SAR has a nearly all-weather capability, a day or night capability. The signal can penetrate through a medium, whether that's a vegetation canopy, whether that's a soil or snow. There are minimal atmospheric effects on SAR images, so you don't have to do an atmospheric correction as you would on optical images. And basically, radar is sensitive to structure, surface structure, and the water content in the land surface, so the dielectric properties of the land surface. That means surface wetness or liquid versus frozen state of the land surface. The disadvantages is that the information content in radar images is different than optical, and sometimes it's difficult to interpret. And also you have to account for the effects of topography on radar images, as well as the effects of speckle, which is that graininess in the images. So there are two main types of remote sensing observations. In general, passive and active, and that applies to microwave remote sensing. So there are passive microwave sensors, and they're called radiometers. So they measure energy emitted from a medium in the microwave range or in a specific part of the microwave range. And then there are active sensors, and these sensors provide their own illumination source. So a radar is an active sensor. And the instrument emits a burst of energy, and that same instrument measures the portion of the signal that is reflected back. So active remote sensing in the microwave range is called radar remote sensing. So here we're just focusing on the active radar remote sensing. And so radar is essentially a ranging or a distance measuring device. And there are two categories of radar, the imaging and non-imaging radar. So for example, an altimeter is a non-imaging radar. Synthetic aperture radars are imaging radars, and they are always side-looking because if the radar would be looking straight down, such as the figure that you see on the left, you would not be able to differentiate between 2 points, in this case A and B. The signal would reach point A and point B at the same time and return to the sensor at the same time, which is why you wouldn't be able to differentiate them. However, if the radar is side-looking, such as the figure on the right, the time that it takes for the signal to reach point A and point B is different, and therefore these 2 points can be resolved. A radar transmits short bursts or pulses of microwave energy at regular intervals, and the radar beam illuminates the surface obliquely at a right angle to the motion of the platform. The antenna then receives a portion of the transmitted energy reflected, or what's called backscattered, from various objects within the illuminated beam. And by measuring the time delay between the transmission of a pulse and the reception of the backscattered echo from different targets on the ground, their distance from the radar and thus their location can then be determined. So as the sensor platform moves forward, recording and processing of the backscatter signals build up a two-dimensional image of the surface. Now, the range or the across-track resolution is dependent on the length of the pulse, and the azimuth, or what's called the along-track resolution, is determined by the beam width, which is inversely proportional to the length of the antenna. So that means that a longer antenna will produce a narrower beam and finer resolution. Since it's really difficult to have very long antennas in space, one can be synthesized by using the movement of the satellite or the aircraft to simulate a very long antenna. So that's why it's called synthetic aperture radar, which allows for high-resolution images with comparatively small physical antennas, and through the use of signal processing of the Doppler shift associated with the motion of the platform. Most radars measure amplitude and phase, and amplitude is the strength of the reflected signal, and the amplitude is the backscatter coefficient. It's also known as sigma naught, which is the fraction of incident energy scattered back to the antenna per unit target area. Sigma naught is expressed in decibels, and you do this by taking the log 10 of the energy ratio. And that value usually varies between minus 30 dB, so that's low backscatter, or little energy reflected back to the radar, to around 0 or 1 dB, which are high backscatter or bright tones on the image. So that's a large amount of energy reflected back to the radar. Phase is the position of a point in time on a waveform cycle, and it's measured in angular units like degrees or radians. In today's session, we will just be dealing with the amplitude. However, in the second session on landslides, we will be dealing with the phase, and Dr. Eric Fielding will provide a refresher on the phase and interferometric synthetic aperture radar. So next, we'll discuss the radar signal interaction with the land surface as related to flooding. So first I'll define flooding from a radar perspective, and it refers to two different kind of conditions. One is a water surface beneath a vegetation canopy, regardless of whether it's a forest or agriculture. So when I refer to an inundated forest, it means that underneath the vegetation canopy, there is standing water above the soil surface, as shown in the image on the top left. In agricultural or herbaceous areas, the leaves or stems of the plants visibly emerge above the water surface, as shown in the bottom center figure. Now, something to remember is that the radar just detects standing water, but not the amount of water above the surface. You can have 1 centimeter of water above the surface or 1 meter of water above the surface. The radar signal response will be the same. Radar can also detect flooding where there is no standing vegetation, as you can see in the image in the top right, and I will refer to this as open water. When the radar signal is emitted, it interacts with the land surface in different ways, and these are called backscattering mechanisms, as shown here. Specular scattering on the far left occurs when there is a smooth surface or a mirror-like surface, such as a calm water surface or an asphalt road, and the signal then scatters away from the satellite, resulting in open water appearing as a dark pixel in the image. The next one is rough or diffuse scattering, which results when there's some roughness on a surface, causing the signal to scatter in different directions, but mostly away from the satellite. And an example of this would be a water surface that has some level of roughness caused by either floating vegetation or wind. And it can also be like a recently tilled agricultural field. But such an area would appear dark, but not as dark as a water surface that is completely smooth. And the rougher that surface gets, as shown in the next figure, the larger the signal scattered back to the satellite, and the brighter that pixel will appear on the image. And then the next signal interaction is volume scattering, and that occurs when the signal is scattered multiple times and in multiple directions within a volume or a medium, which could be a snowpack, soil, or vegetation. And in the case of vegetation, the signal can scatter from multiple components such as branches, stems, leaves, trunks, or soil. And then the final backscatter mechanism is called double bounce, and this results when two smooth surfaces create a right angle that deflects that incoming radar signal off both surfaces, causing most of the energy to be returned to the sensor. And these areas appear very bright in the radar images and are commonly seen in flooded vegetation because of the interaction between the smooth water surface and vertical structure of the vegetation, such as the trunks. Double bounce in flooded vegetation occurs regardless of whether, again, there's 1 centimeter of water or there's 10 meters of water. And it also occurs in urban areas. So these are common sources of confusion. If you're looking at flooding and there's an urban area, it's also going to look like it's a flooded area. And I'll show you some examples of that. So this is an example of SAR signal scattering over an area that has significant flooding. So this is an L-band HH polarized image from the Japanese PAL-SAR sensor on board the ALO satellite over an area near Manaus, Brazil. And the areas that I've circled in green, or the area I've circled in green, is volume scattering. So that's forest. So that's like a gray tone. The areas that are relevant to flooding are really the dark areas. So that's open water. Remember, that's specular scattering. And an example of that is the blue circle. So that's the Amazon River. And then an example of double bounce, which is flooded vegetation, are all of those really bright white areas. And an example of that is the purple circle that you see here. So the striking part about this image is that in some areas you cannot see the specular scattering from the river because it's either too small or it's covered by vegetation, but you can still see its extent through flooded vegetation because the signal is penetrating through the vegetation canopy and double bounce is occurring. And this level of detail in detecting flooded vegetation is truly unique to radar. It's not something that you can detect with optical images. There's different types of radar data, and depending on the characteristics of the sensor, you might be able to better detect flooded or inundated vegetation. So let's discuss some of these parameters, both radar and surface parameters that you should take into account. So there are radar parameters and surface parameters, and I'll discuss these in the context of flooding with the radar parameters. So there are 3 radar instrument parameters that influence the transmission characteristics of the signal, and these are wavelength, polarization, and incidence angle. Let's talk about wavelength. There are 2 important things to remember about wavelength. And the first is that the longer the wavelength, the greater the penetration through the medium. And the second is that the length of the wave will determine the interaction with surface objects. So the wave will interact with objects that are approximately its size. So if an object or surface roughness is the approximate size of a wave, then there will be interaction, and the surface will appear rough, and there will be energy scattered back. So for example, if an L-band wave on the order of 24 centimeters encounters a surface with a height fluctuation on the order of 5 centimeters, there'll be minimal to no scattering with that surface. To the L-band signal, that surface will appear smooth, and in the image that pixel will appear dark. However, if the signal interacting with that surface is a C-band signal with a wavelength of around 5 centimeters, then that same surface will appear bright due to increased backscatter. Now, the figure on the left shows the extent of penetration through different mediums with different bands. X-band sensors, for example, TerraSAR X, in general have limited penetration through dense vegetation. However, there have been some studies that show the potential of X-band to identify flooded vegetation for areas where there's sparse vegetation or during leaf-off conditions. So in that case, the signal penetrates through the canopy, through the gaps in the canopy. And you will see double bounce in areas where there's inundated vegetation. C-band penetrates further into the canopy, and then L-band penetrates even further into the canopy. So really, the preferred wavelength for looking at flooding is L-band, for looking at flooded vegetation. But C-band can work well, especially in agricultural areas. Here we have an example of signal penetration through vegetation to detect flooding. So remember, flooding is dominated by double bounce. So flooded vegetation is dominated by double bounce in radar images. And those appear as very bright areas. So here we have an area in a SAR image for an area in Manu National Park in Peru in 1993. And we have 3 different frequencies: C-band, L-band, and P-band. C-band is around 5 centimeters, L-band around 24, and P-band around 60. And you can see that there are more bright areas or flooded vegetation as the wavelength increases. Right, so you can see more flooded vegetation at P-band than at L-band or C-band. Polarization refers to the plane of propagation of the electric field of the signal. And this can be in the horizontal plane or in the vertical plane. And irrespective of wavelength, radar signals can be transmitted and or received in different modes of polarization. And there are 4 combinations of both transmit and receive polarizations. Those are HH, so horizontally transmitted, horizontally received; VV, vertically transmitted, vertically received; or HV and VH. Penetration depth is influenced by polarization. So in forests, HH tends to penetrate deeper into the canopy because it tends to be less attenuated than VV. And HV is more sensitive to volume scattering, and it's a really good indicator of vegetation cover. And this is an example of using multiple polarizations for detecting inundated vegetation. This is L-band from Pausar over Pacaya Samaria in Peru, which is a wetlands complex. And you can see much more flooding or flooded vegetation with the HH polarization than with the VV. And with HV, you're not really detecting much flooded vegetation at all. So HV tends to be more sensitive to the presence of vegetation. And the reason for that is because the signal tends to depolarize. That means change polarization, right? When you have multiple scattering mechanisms. So whenever you have like a volume, like a vegetation canopy, and you have multiple scattering mechanisms where the signal scatters from one component to another, there's a lot higher likelihood of the signal depolarizing. And so that's why cross pole or something like HV or VH is more sensitive to volume scattering in the presence of vegetation. So here we have an example of multiple polarizations for detecting open water. And this is L-band, and we have HH, HV, and VV. And so HV is the best polarization for detecting open water. Now, the reason for this is because the signal does not depolarize well in open water, right? So remember I mentioned that the more times that signal scatters, like when you have a volume, like a canopy, the more times it scatters, the higher the likelihood that that signal will depolarize. Well, in the case of a smooth surface like open water, it doesn't scatter multiple times, and that's why the signal does not depolarize, and it tends to be very low with HV. With HH or VV, there's some level of scattering on the water maybe, and so that's why it looks a little, there's some level of roughness, and the backscatter is a little higher. But with HV, it really does not depolarize, and it remains very low. And the final parameter to account for is incidence angle. So that is the angle between the direction of the incident wave and the Earth's surface plane. And in radar, the incidence angle increases across the swath from the near to the far range. And large angles will be more sensitive to surface roughness and will penetrate less into the medium as opposed to small angles. So low incidence angles will result in higher backscatter and greater penetration. So lower incidence angles are better at detecting, say, inundated vegetation. So we talked about the radar parameters. Now we'll move on and discuss the surface parameters. So what are the parameters in the surface that influence the signal? And those are dielectric and structure. So there are three parameters related to structure. There's density, there's size relative to wavelength, and then there's orientation. The size of your structure will determine whether the surface is rough or smooth, and a smooth surface will appear darker and rough surfaces will appear brighter. So there's size and orientation, and that influences the interaction of the waves that are either horizontally or vertically polarized. And then there's density, the density of the scatterers, and that influences the strength of the signal, making for a stronger signal when the scatterers are closer together. And this is an example of size relative to wavelength. So at X band, which is a wavelength of around 3 centimeters, we're looking at the components of the vegetation that are around that size. At L band, in this case around 27 centimeters, looking at components of the vegetation that are around that size. Now in this case, it would be more of like the branches and the twigs. And then at P band, which is even a longer wavelength, we're looking at the larger components of the vegetation, so the longer branches and the trunk. And finally, size and orientation. So the signal will interact, the polarization of the signal will interact with the components on the land surface that are polarized, that are oriented in the same way. So a vertically polarized signal will interact with vertical components of the land surface. If it's vegetation, it'll interact with the vertical components of the vegetation. So that would be primarily the trunk, or if it's a leaf that's angled, well, the vertical component of that leaf. And the same case for horizontal. And then there's vegetation density. So in general, the denser the vegetation, the less the penetration. Right, so at C band, so that signal saturates, and at C band in a boreal forest, in this example, the signal saturates at around 20 tons per hectare, at L band at around 40 tons per hectare, and then at P band at around 100 tons per hectare. And then there's the dielectric constant, and this is the water content in the land surface, so in the vegetation, in the soil, and whether this water is liquid water or frozen. So if you look at the dielectric between something that's dry, it's on the order of no more than 10. And the dielectric of water is 80. So whenever you have liquid water in the surface, in the components of the surface, there's high reflectivity. So that signal will reflect will have a much higher reflectivity than if your surface would be dry. And so that's why the signal penetrates much better when you have dry soil. So it'll penetrate more through dry soils or through frozen or dry vegetation as opposed to wet soils or wet vegetation. So now I'll discuss some of the effects of topography that you need to account for, as well as speckle. And these are geometric distortions. So one of them is layover, and that occurs when the radar beam reaches the top of a tall feature, in this case B, point B, before it reaches the base, point A, on the figure on the left. And the return signal from the top of the feature will be received before the signal from the bottom. And as a result, the top of the feature is displaced towards the radar from its true position on the ground, and therefore it lays over the base of the feature. So layover is most severe for small incidence angle at the near range of a swath and in mountainous terrain. And then we have foreshortening on the figure on the right, and that occurs when the radar beam reaches the base of a tall feature that's tilted towards the radar, so for example a mountain, before it reaches the top. And because the radar measures distance in slant range, the slope A to B will appear compressed, and the length of the slope will be represented incorrectly. So depending on the angle of the hillside or the mountain in relation to the incidence angle of the radar beam, the severity of foreshortening will vary. And some of these things can be corrected using a digital elevation model. So this is really due to that side-looking nature of radar. Then there's radar shadow, and that occurs when the radar beam is not able to illuminate the ground surface. And the shadow occurs wherever you have complex topography. And since the radar beam does not illuminate the surface, the shadowed regions will appear dark on a radar image because no energy is available to be backscatter. And there are ways to correct for shadows through interpolation, but I personally leave the shadow areas as areas of data gaps rather than use interpolated values. And then the last aspect to discuss is speckle, which is a grainy salt and pepper texture in radar images, and that's caused by the random constructive and destructive interference from multiple scattering returns that occur within each resolution cell. So as an example, if you have a homogeneous target, such as, say, a large grass-covered field, without the effects of speckle, it would generally result in light-toned pixel values in the image, as in what you would see in the case of A, in the far right. But in radar images, the reflections from individual blades of grass within each resolution cell results in some images being brighter and some pixels being brighter and some being darker than the average tone. And that field will appear speckled, as you see in image B on the far right. So one way to reduce speckle is to apply a filter. And it consists in moving a small window of a few pixels in dimension, and that's all user-defined. Could be 3 by 3, 5 by 5. And you move this over each pixel in the image, applying a mathematical calculation using the pixel values within the window and replacing the central pixel with the new value. And the window is moved along in both the row and column dimensions 1 pixel at a time until the entire image has been covered. And by calculating, say, the average of a small window around each pixel, then there's a smoothing effect achieved and the visual appearance of the speckle is reduced. Now, spatial filtering reduces speckle at the expense of resolution, and therefore the amount of speckle reduction desired must be balanced by the particular application the image is being used for and the amount of detail required. So if you require like really high resolution, you might want to use a very small filter or window. And if it doesn't hurt you to reduce spatial resolution, then you can use a larger window. But in the end, if you're running, say, classification, that speckle, that graininess will translate into your final product. Another way to reduce speckle is to do a time series averaging. So if you have multiple radar images, you can just average them, and that will also reduce the speckle and preserve your original resolution. And then there are the confounding factors. So what sort of issues cause confusion when you're trying to identify flooded areas? So sources of confusion when detecting or when identifying open water, and that can be low vegetation. And so open water is a specular reflector, but if you have any sort of roughness on the water because, say, of wind or short vegetation, then that will resemble areas on land that have very low backscatter, such as a tilled field or maybe a bare field. And then there's also confusion between urban areas and flooded areas. And here, the area that's circled in red, that's the city of Manaus, which has a very high backscatter. And then the flooded areas along the river that are white, those are areas where there's inundated vegetation. So the scattering mechanisms in areas where there's flooded inundation vegetation and urban areas is the same. That scattering mechanism is double bounce. So these tend to be confused, and the best way to resolve these is if you have any sort of prior information about where the urban centers are located, for example, and if you have a shapefile that you can mask out those areas. And another source of confusion when detecting flooded vegetation are areas of complex topography. So they tend to have high backscatter as well. And so a way to lower this confusion or remove this confusion is to use a digital elevation model and then mask out the areas of complex topography by either applying an elevation threshold or applying a slope threshold. And then one last thing to be aware of when analyzing images and using images to look at, say, flooding and flood extent is that sometimes rain events can have an impact on the images. So at C-band, C-band is on the order of 5 centimeters. So Sentinel-1 images, which are the images from the European Space Agency, the ones we'll be using today in the demo, they're C-band. And sometimes when you have like these really heavy rain events, these rain cells, the large amount of water in those cells can attenuate the signal. And so you have weird artifacts in the image. So here's an example of a rain event where you have attenuation and you also have like really wet soil, so you have a greater reflectivity. And so you have these weird features. So it's always good to take a look at your images and make sure that that you don't have any of these weird features that might throw off any sort of algorithm that you might be applying to generate a product. And finally, I want to touch on what sort of radar data is available. Currently, only Sentinel-1 SAR data is operational and freely available. There are some historic SAR datasets, such as Pulsar-1 from the Japanese Space Agency, and that's L-band, and then there's ERS from the European Space Agency, which is C-band. There are also upcoming SAR satellites in the future, such as Biomass. It's a P-band sensor from the European Space Agency, and I believe that's scheduled to be launched in 2023. And then there's NISAR, which is which will have an L and an S-band sensor, and that's a joint collaboration between NASA and the Indian Space Agency. And that's scheduled to be launched in early 2024. And there are several ways to access SAR data for free. The Alaska Satellite Facility is an excellent resource. You can access Sentinel-1 data, you can access Pulsar-1 data, and several other SAR, historical SAR data sets. You can also access SAR data, specifically the Sentinel-1 SAR data, through the ESA, the European Space Agency's Copernicus hub. And you can access the SAR data from Sentinel-1 through Google Earth Engine, which is what we'll be doing today. But these three resources, they're all free. All you have to do is sign up and have an account, and you can download the data for free. So the processing steps for SAR data to be analysis ready are to apply a radiometric calibration, a geometric calibration to do the terrain correction using a digital elevation model, and then you apply a speckle filter. Now, in the case of using Google Earth Engine, Sentinel-1 on Google Earth Engine, the data is already analysis ready, except it hasn't been speckle filtered, but we'll walk through that in the next couple of slides, or once we get in the demo. And now we'll begin our flood mapping demonstration, which will be done in Google Earth Engine using Sentinel-1, which is C-band data from the European Space Agency. So for those of you not familiar with Google Earth Engine, it's a cloud-based geospatial processing platform, and it's free. All you need to do is sign up for an account. It's based on a JavaScript code editor, and there is a catalog of satellite imagery and geospatial data sets that can go back a couple of decades. So in the case of, say, something like Landsat optical data, it can go back a couple of decades. So it's a really powerful resource to be able to have all of these data sets in the cloud and to work and do your analysis on the cloud rather than downloading the images to your computer directly. So this is the Google Earth Engine code editor. On the far left, you've got your script manager. You've got documentation on the different functions that are available to you, and then you have your asset manager where you can upload images or shape files. In the middle, you've got your code editor, and on the far right, you've got your task manager, your console output, so you can output information about the images, or you can output graphs, for example, and you can inspect your image and print out pixel values or the location of a pixel, etc. So as mentioned, today we'll be working with the Sentinel-1 data, and just for your information, Sentinel-1, again, it's a European Space Agency satellite. There are two Sentinel-1 SAR satellites, A and B, or there were two. One is recently became non-operational. They're both C-band. Each satellite has global coverage every 12 days, and between the two of them, there's 6 days. So up to a couple months ago, there was coverage between both of them, but now it's just one. So it's a 12-day temporal repeat. They have different modes of data acquisition, and the one that is used for studies over land, the routine collections for land, is the interferometric wide swath. The Sentinel-1 catalog on Google Earth Engine has Sentinel-1 data starting from 2014. So Sentinel-1A was launched in 2014, Sentinel-1B in 2016. And Sentinel-1B, as mentioned, it's no longer operational as of December, mid to late December 2021. The data, however, all of the data, Sentinel-1 data on GE is pretty much analysis ready. The only thing you have to do is apply a speckle filter. And so the following steps have been applied to the data using the SNAP toolbox, and that's a thermal noise removal, radiometric calibration, and then terrain correction using a digital elevation model. The data are also in dB, so they're in logarithmic values in decibels to represent backscatter. So it's sigma naught. And the resolution is 10 meters, and the interferometric white swath mode is two polarizations, VV and VH. Our demonstration today is focused in the state of Kerala in India, where due to unusually high rainfall during the monsoon season in August of 2018, there were severe floods. In fact, they were the worst floods in Kerala in nearly a century, and it caused many deaths, evacuation of thousands, millions of people, and loss of infrastructure. So what we'll do today is use Sentinel-1 images, multi-temporal Sentinel-1 images, to map inundation extent and see how the water receded through time. Here's the code that I ran today, and you can modify this for your area of interest and events of interest. All right, so let's start our demo. This is the Google Earth Engine code editor. I know many of you are probably familiar with this, but just to give you a brief overview, here on the left, you've got the scripts. So this is where I keep all of my different scripts and docs that basically has a documentation of all of the different functions within Google Earth Engine. So if you want to learn about any sort of functions, so for example, a classifier, you can go in and click on it or do a search for one, and it'll provide more information about each of the different functions and how to run it. And then assets, you can upload your own individual files, whether they're raster or shape files or CSV files. So that's just a small overview there of what's here on the left. In the center is where you type in your code, and in the right, you've got three tabs, inspectors, so you can click anywhere on an image and it'll provide the value for that pixel as well as the location. And then console, you can print out results of your analysis onto the console. And then tasks is where you export your image. So you initiate the process of exporting an image. All right, so let's keep it in console and let's start with the code. The objective here is to look at flooding in Kerala in India during 2018, so during the monsoon floods of 2018, August 2018. And we will be looking at several different dates and compute the flood extent during each of these different dates. So we will be computing this flood extent according to hectares, so the area of that flood extent. And we will go a little further. We will also integrate, sorry, just to step back. To compute the flood extent, we will be using a threshold. And we will also then bring in a crop map, a land cover map of crop area, and we will take a look at where there are crops and where there was flooding to then also estimate the crops or the cropland that was affected by the floods. So there are a couple of different components here to this code, and I will walk you through all of that, including labeling your final product and with a legend and a description, and then exporting your results both as a TIFF and as a shapefile. All right, so let's start with the very top. All right, so the first thing you want to do, let's zoom into our area of interest. It's here in Kerala in India, and you need to define your area of interest. And so to do that, you go under Geometry Imports and you click on New Layer, and then you click on either this icon, which is a draw a shape or draw a rectangle. Let's draw a shape, and you define your area of interest. Let's define that as our area of interest. and then you go and you name it. You call it area of interest or region of interest. In this case, we're calling it region of interest, all right? But I'm not going to do it because I already have it, but these are the steps that you would need to go through. So in fact, I am just going to erase it, what I just did. And this is the region of interest that I defined. Now, it can be user defined, or you can also use a shapefile. So for example, and I added it here as optional, here on the top, you can call a shapefile that has level 1 administrative levels. So that would be at the state level. And in this case, if you uncomment this, you can then pull out the shapefile for the state of Kerala in India. All right, so I didn't do that, but just so that you know, you can do this as an option, or pull out the state of any other state in India or any other country that you're interested in. So to uncomment, anything that has 2 forward slashes means it's commented. So to uncomment anything, just delete those forward slashes. Okay. And all of the comments, make sure you leave all of the comments commented. Otherwise, you're going to get an error in your code. All right. So then one of the things I did is I set the Google terrain as the base map. And the reason for that is it's kind of nice to have a good sense of what the terrain is. So you don't have to have this, but you can always comment it out if you like. So the next thing we do is we do a search through the Sentinel-1 database. And that image collection is called Copernicus S1 GRD. So how do I know how it's called? Well, if you're not sure, just go into and do a search up here, say Sentinel-1, and it will bring up a description of the Sentinel-1 data that is on Google Earth Engine. So it's a description, the bands, the image properties, terms of use, etc. But here is the code to call that specific database. Okay, so that is what we're calling. And here within our search parameters, we're specifying that we want the images that have been acquired in the interferometric wide swath mode. So that's IW, that's the common acquisition over land. We want orbital pass, a descending orbital pass. If you do a search for a different area of interest and you find very few images for your area and time of interest, then change to ascending, and maybe you will find more images over your area of interest. Okay, so in this case we're using descending because I know already that there are more images in the descending path than in the ascending. I did this test already. The images are all 10 meter in spatial resolution. The dates, so we want to find images that fall within this time range. That would be August 1st of 2018 through early September of 2018. And the bounds, the region that I'm looking at is the ROI. So this would be my ROI. And then I am printing those results onto my console. So let's see what happens. So we run the code. And here in the console, I have something that's called Sentinel-1 collection. So if I open that, it says features 8 elements. So that means there are 8 images that were found within my filter bounds, within everything I specified here. And these are the 8 images. So you can see that the dates are August 9th. There are 2 images that cover my area of interest on August 9th, 2 images that cover the area of interest August 21st, September 2nd, and then 2 images that cover my area of interest on August 27th. Now, these are not in order. The reason for that is because the first 6 images are from Sentinel-1A, and then the last 2 are from Sentinel-1B. So we'll use all of them. And basically what we're doing here is we are creating a list that contains these images, and then we are pulling these images from that list. Okay, so here's what we do. We are saying, okay, get the first image in that list. So that would be 0, image 0, and then get the second image in that list. So that would be image 1 right here. So those 2 images are both from the same date. And again, we have 2 images because from the same date, because those 2 images cover the entire area of interest that I delineated. So what we need to do is mosaic those images, and that's what I'm doing here in this line number 20. I'm taking what I called image 1 and then image 2, and I am mosaicing them to create now a mosaic image that I'm calling August 9th. So I'm doing the same for the images that cover our area of interest for August 21st, August 27th, and then September 2nd. All right. So I'm creating 4 mosaics, really. 1, August 9th, August 21st, August 27th, and September 2nd. And then I am displaying them. So I'm adding them to the layers bar right here. And in order to add them, this is what you do. You say map add layer, August 9th. Each image, remember, there are 2 polarizations. So there's VV and there's VH, and there's also the incidence angle. So we are extracting, of those 3 bands, we're extracting VH. So we're extracting the specific VH polarization, because in this case, we're looking at inundation. So that's inundation caused by open water. So we're not looking at inundated vegetation. We're looking at areas where there's open water. There's no standing vegetation on it. And VH is a better polarization to detect open water. And then we're calling it, in this case, we're calling it the Sentinel-1 August 9th, 2018 VH. And that's how it's going to appear here on the bar. So that's what we see. If we go all the way to the bottom here, that's that August 9th VH. And then this is August 21st. And you can see there are more dark areas in August 21st. So we're using August 9th as the baseline here. And August 21st, there's quite a bit of flooding in August 21st, then August 27th, and then September 2nd. And you can visualize that. And also what I did here, I was create an RGB. So I combined 3 images to look at the change in a colorful way. So remember the color wheel. So anything that is red, so sorry, let me explain. This is an image, an RGB image from August 9th, August 21st, and August 27th. So August 9th is on the red channel, August 21st is on the green channel, and August 27th is on the blue channel. So anything that is red means that the backscatter was higher on that specific date. So that means it was not flooded. Anything that is red means on August 9th, that area was not flooded. Okay. And anything that is, say, anything that is pink means that it was probably flooded. So that means it's high on the red channel and it's high on the blue channel. That's what pink means. So that means it was probably it was flooded on August 21st, but the water receded on August 27th. So that's how you interpret these RGBs. And it's always good to do these type of just visualizations so you can understand and interpret the images. So anything that is, say, green, that means backscatter was high on the image that is on the green channel. So backscatter was high on August 21st, and it was low on August 9th and August 27th. And anything that is blue means that backscatter was high just on August 27th and then low on August 21st and August 9th. Okay, so you can pan around and just interpret the image according to the colors that you're seeing. And also here, I did another RGB for the dates August 21st, August 27th, and September 2nd. All right, so let's carry on with the rest of the code. The next thing I did here was apply a speckle filter. And this is just a mean and average filter, speckle filter. And this determines the size of your filter. So I used a size of 30. You can go bigger, you can go smaller. Obviously, the bigger you go, the greater the reduction of speckle, but the greater the reduction in spatial resolution. All right, so then we used the speckle filtered images to create these difference images. So we subtracted the after image from the before image. Okay. Now, one thing to keep in mind is I'm subtracting, but because these images are in dB, in decibels, which are logarithmic values, you actually divide. You do a division. Okay, so I'm doing this for using August 9th as a reference, right? So I'm subtracting each date to August 9th. So August 21st to August 9th, August 27th, and then September 2nd. And then I am visualizing, I'm adding to the map layer just one of them so you can kind of have an idea of what that difference image looks like. And that's interpreted. So the areas that have a very high values are areas where there has been a change. So where it was, where there's been inundation, those are the areas where there's high values. And to have an idea of what those values might be, go to Inspector up here on the top right, and then click somewhere where it's high. Let's click right there. And I'm actually getting the values of everything that's under my layers here. But let's go down and take a look at, okay, so let's start here. It's giving me, for that pixel that I clicked on, it's giving me the value for the August 9th image, for the August 21st image, 27th, September 2nd. Okay, so this is the RGBs that I created. And this is the difference. So the value for this difference image is 1.63. And you can just click around if you want to get a sense of what the different values are. So the next thing I did was I created a threshold, right? So I know that the bright values are areas where there's inundation. And I define the threshold, and this is purely trial and error, okay? I defined the threshold of 1.25, and I said, okay, anything greater than that threshold for each of these difference images, is considered inundation. And then again, let's see, this next layer is the flooding extent for just August 21st. So the reason I did this is because I want you to see what the initial pass looks like, okay? So anything that is black are areas where there is inundation that are considered to, there's a change between August 9th and August 21st in terms of a decrease in backscatter, which reflects inundation, open water inundation. All right, so you can see this image that it's very noisy. Even though we're using the filtered image, there's a lot of noise here. So one of the things we want to do is clean it up. And if you visualize the other flooded images for the other dates, you'll see that they look very similar. There's a lot of noise. There's even change here. It's picking up inundation over permanent water bodies. So let's go ahead and refine those results. The first thing we do is we calculate pixel connectivity, and we remove those connected by 8 pixels or less. So anything that is a bundle of 8 or less pixels, we're removing them. And we're doing this for each date, okay? For August 21st, August 27th, September 2nd. You can play around with this. You can say, okay, well, anything connected by 5 pixels or less, or 10 pixels or less, however you want. And then I've added it to the map, to the layers, so that we can then visualize this next level of cleanup. Okay, and this is just the August 21st image. So and it's in red. Okay, so you can already see a difference there, that there are less red pixels or areas than black areas. So there's been some level of cleaning that has occurred just by looking at the pixel connectivity, but there's still noise that we want to deal with. All right, so let's apply another level of refinement here. And what we'll do is we'll remove misclassified pixels in areas where the slope is greater than 5%. And for that, we'll use an SRTM, digital elevation model. So in order to call that SRTM DM, we use, this is the data set on Google Earth Engine. And so we identify the slope, and then we say, okay, anything that is less than 5% slope, we keep. Anything above that, we eliminate. All right, so here I've commented out, but you can change this if you want to actually view the SRTM for the region of interest. And here I've added the next refinement of the flood extent as pink, okay? So the first refinement was in red, and that was eliminating the pixels that were, or the areas that had 8 pixels or less, and now we're eliminating the flooded areas where there is topography. And this is why I like to show the base map as a terrain, because it gives you an idea of where that terrain is. And then this is just for August 21st, and this is just for visualization purposes, because these are intermediate products that we're generating, and I just wanted to show you the difference between one refinement and another, as we keep doing these refinements. So The red area, especially in areas where there's topography, like here, you'll see that in the next refinement with the SRT-MDM, those red areas disappear. Okay. All right. So let's keep working down our code. The other thing that we want to clean up are misclassifications over permanent water. And you can see that there are pixels that are being misclassified in areas where there's permanent open water. So what we want to do is we want to use a land cover map. And in this case, we're using the Copernicus Global Land Surface Land Cover Map, CGLS. And we will then mask out areas where that map identifies that there is permanent open water. So the first thing we do is we call that map, and that's this one. And we will, it's the discrete classification, and we will clip it to our region of interest. And we will then identify the classes that we're interested in, which are open water related. So these are inland open water bodies, and this is ocean water. And to know more about that, just go in and type CGLS to know what the different class values are. And up will pop a window, and you will select this one, collection 3, and then under bands, scroll down. And here's a description of all the class values. So I've done this already, so I know that class value 80 are permanent water bodies. These are inland water bodies. And then that class number 200 is ocean. Okay. Or can be either fresh or salt water bodies. Okay. So what I'm saying here is to identify in that land cover map the regions, the pixels that have a value of 80 or 200. And then we're saying, okay, anywhere where there's inundation in those areas where it's equal to 80 or 200, make that equal to 0. And I'm doing that for each of our dates, August 21st, August 27th, and September 2nd. And then I'm adding those layers to that new refinement to the layers. And this is now considered the final refined flood extent map for each date. Okay, so if we go in and just to show you the example of August 21st, the previous refinement where we filtered out the misclassified pixels in areas of having a slope of 5% or more. And then this one, you can see that the misclassifications over open water bodies have been cleared up. So those areas disappeared. So we still have some remnants here. So let's take a look at the land cover map that we used. And interesting, so in these areas where there is green, so there is flooding being detected, those areas, according to the land cover map, those are mangroves or wetlands. And I know that because if you go to Inspector and you click on that pixel, it'll give you the value for that pixel. So we go in here into land cover, it says that the value for that pixel is 90. And again, if we go back to our data set and we look at the values of the bands, we can see that 90 are herbaceous wetlands, herbaceous or woody vegetation. So that's probably a wetland that has been inundated. Okay. So let's And just for visualization, then August 21st is the flood extent on, whatever's green is the flood extent on August 21st. Whatever is yellow is the flood extent on August 27th. And then whatever is orange is the flood extent on September 2nd. So the next step here was to calculate the inundation extent. And the way I did that was to sum all of the pixels for each image that were classified as inundated. And then we know the native spatial resolution of Sentinel-1, which is 10. And then we converted that to hectares. Okay. And we printed it out on the console here. So let's go back to our console, and we printed out the hectares of inundated area for each date. So you can see hectares of inundated area for August 21st, August 27th, and September 2nd. So the max inundated from these three images was on August 21st, a little less on August 27th, and even less so on September 2nd. So the next thing that I did here was to look at the cropland that was affected by these floods. And for that, I used the same land cover map as the one to identify permanent water bodies. So that's the CGLS again. And in this case, identified the croplands. Okay, so this is the land cover map. And croplands are anything that is pink. Okay, so if you just want to take a look at cropland, that's cropland. So what we did here was identify where there was crop and where it was inundated. So the intersection of those two then meant that that was an inundated crop, and created an extent of cropland, a flooded cropland extent for each date, and again also calculated the statistics of inundated cropland area in hectares and printed it out here to the console. So I did this for each date. The first one is August 21st. Here we do exactly the same thing for August 27th. And here, and the next one is September 2nd. And I printed out here, you can see the hectares of inundated cropland on August 21st, on August 27th, and on September 2nd. And again, it's the same trend as you see as total flood extent. There is a maximum hectares of inundated cropland on August 21st, less so on August 27th, and even less so on September 2nd. So the next part here was to make these maps nice and add a legend and a description of the results. So I'm not going to go into this, but this is how you, the code to add a legend. And you can modify this and change what you want to write out, but really it just explains the colors and the results. So let's run this. Oops. Okay, so here is our legend, flood extent on the different days. So this is just a total flood extent. This is not the flooded cropland extent, but you can add that if you'd like as well. And let me just go up here. So I'm gonna use, if you change the 0 to 1, it will automatically pop up that image on your map when you run the code. So it's nice to have a reference SAR image with the results of total inundation for the different dates. Okay. So again, these are the final refined inundation products for the different dates. And I put a 1, so that means when you run it, it will automatically show the results. You don't have to go into your layers and activate it or to pop it up. All right. So going back to our legend, here's how you create that legend. And then also a description of the results. So this has a description of the total number of hectares in terms of total flood extent and flooded cropland displayed on the bottom left. And so I'm just gonna make sure that displays. There you go. So these are your results, and this is a code that you can use in other areas of interest and for other events. So this is just an example. These results have not been validated, and I do want to give a shout out to UN Spider, because parts of this code were adapted from a UN Spider flooding script that was presented back in December of 2019. So the last part of this code is to export your results, and I've given examples here of exporting your results both as a raster and as a shapefile. So the first example is a raster, exporting it as a geotiff. And scale here represents the resolution, so that is the native resolution of the Sentinel-1 imagery, so that's 10 meters. And then here, in order to export it to a shapefile, you first have to convert your rasters to polygons. So you go through this process, and then you export those polygons to a shapefile. And then in order to actually download those, you go to your Tasks tab here on the top right. You click on it, and you have these tasks waiting for you. So basically, I need to initiate exporting my files, both the vector and the raster. So to do that, I just click on Run, and it might take a little while, but it will be placed on my Google Drive. And it just, it depends on how big your image is. It might take a little while. If for some reason it hangs, you're going to have to change the spatial resolution to make it smaller. Or you might need to cut your image. So that's it in terms of this example. I hope that you've learned something new. Again, the code for this code is on the PowerPoint presentation, so you can run it, change it, adapt it to your particular event, region, and time of interest. So before I finish, I just wanted to make you aware that I've included an appendix to this presentation, and it includes a list of SAR tutorial references, as well as valuable resources. And these are all free and open for people that might want to dive a little deeper into into learning more about SAR and being more connected with the community. The first couple of slides have links to the ARSET SAR tutorials. The Alaska Satellite Facility has many, many incredible resources. They have teaching material, they have data tools, data recipes, They have ways to process the data, your data on the cloud. It's very valuable, and I suggest you go and visit their website and take a look for yourself, all the resources that they have available. And there's also the SAR Handbook, which was published by Servier, and it is a book with different chapters focused on methodologies for forest monitoring and biomass estimation. Another really wonderful resource. I also have links here to other resources, whether they're documents or videos, really excellent resources from a variety of different sources. Some are from the European Space Agency. They have a wonderful video tutorial called Echoes in Space. The Canadian Space Agency also has some really great documentation and tutorials on SAR. So there's a couple of really great references in the next 2-3 slides here. And then finally, I'd like to make you aware of a group called Sisters of SAR, this group is doing a wonderful job in creating awareness, not only about what is being done with SAR, both science and applications, but also who's doing it. And they have a website, and the website has some really great resources. In fact, they have a SAR resources link at the top of their page. And there you can, they have a very comprehensive list of different tutorials, both documents and video tutorials, covering different levels of SAR for people wanting to learn more. And they're also on Twitter and LinkedIn. Here's my email address. Please feel free to contact me should you have any questions. And we've also included the training webpage for this webinar series, as well as the webpage for the ARSET website and our Twitter handle. Please enter your questions in the Q&A box, and we will answer them in the order they were received. We will post the Q&A document to the ARSET training website following the conclusion of this session. That concludes this session. Thank you very much. We have been gathering your questions, and we will now begin our question and answer period. For those asking about the code, just to let you know that the code is on the PDF presentation that you can access through the ARSET training page. So we've been collecting some of your questions already, and I'll just start going through them. Let's see. The first question is, why use descending paths for flood mapping? Can we use the ascending paths? And I just wanted to share my screen here. Let me see if I can do that. Yeah, I can't quite share my screen, but absolutely, you can use ascending passes. And what you do is you go to that part of the code where I wrote descending, and you change that to all capitals, ascending, and just run your search. The reason I use descending is because I already took a look at the coverage over this area of interest for descending images and for ascending, and I determined that there were more images with the descending pass than with the ascending pass. All right, but this is something that you need to explore for your specific area and time of interest. All right, the second question, can someone please explain how the RGB was created? I don't see any code for it. So let me just try here. Please be patient. Let me try to share my screen. Hopefully, let's see, change presenter. And okay, And all right, so here you can see my screen. This is what I was talking about. You change this to ascending, and you run your code. Okay. Okay. So, okay. So let's go down and answer the question about the RGB. Here's where I created that RGB right here. So I created two RGBs. This is the code. All right, so I'm putting August 9th in the red band, August 21st in the green band, and August 27th in the blue band. They're all VH. I did notice that there was a question further on about what the rest of this code meant. Okay, so min and max. That means how you want to visualize your image, how you want to stretch your values to visualize your image. And let me just so that's purely trial and error, and that's just for visualization, nothing more. All right, while that loads, let's see. Let's just move on to the next question. And I'll come back to sharing my screen. I'm just going to let it load and run. Okay, so the next question is, which polarization is best for mapping partially inundated croplands? What about shallow running water? All right, these are a great question. So I mentioned that the cross pole is better at detecting open water, right? Because open water is a specular scatterer and the signal does not depolarize over specular scatters. So sometimes if you have a little bit of wind and roughness on your water, it might look a lot like areas on land, like say a bare field. But the cross poles are not sensitive to that surface, that roughness on the water bodies. For mapping partially inundated croplands, probably the best polarization is VV if you're using Sentinel-1. Okay, and the reason for that is because you have a higher probability of penetration with VV polarization. Why? All right, let's go back. So let me explain again the cross pole, right? So your signal tends to depolarize, so go from vertical to horizontal when there are many scatterers within your resolution, your illuminated area, right? So if you have, for example, some vegetation, your signal is going to scatter from many different components of your vegetation, from the tree, from the branches to the twigs to the leaves. And so the more times your signal bounces, the higher the likelihood for that signal to depolarize. And so that is why cross polarizations are so good at detecting vegetation, because whenever you have multiple scatterers, there's a high likelihood for your signal to depolarize. And so the signal depolarizes, and there's also less likelihood for that signal to penetrate all the way through the canopy and detect inundated vegetation. When you have VV, you won't have that many bounces of your signal. Your signal will be interacting with the vertical component strictly of what's in the land surface, and therefore it has a higher likelihood of penetrating through the canopy and detecting open water. So that is why VV is a better polarization for detecting inundated croplands. VV if you're using Sentinel-1. If you're using Pulsar, for example, which has HH and HV, and you're looking at forests, you have a higher probability of detecting inundated forests with HH. Okay, what about shallow running water? That's really not going to make a difference if your water is shallow or if it's running or if it's not running. The surface is going to be the same. It's going to be a specular surface, unless you're talking about roughness on the surface, because maybe you've got rapids and things like that. Then again, as mentioned, VH will be a better polarization. The next question, can you please explain the color and the extent of flooding in a greater detail? Like higher the intensity of that color, more the reflection. That makes sense, but does that translate to more flooding on that particular date? Yes. So let me go back. Let me load my code and make sure it's running. All right, so I'm gonna try this again. Okay, so let's go down to the code, and the higher the intensity of the color. Okay, so what I've created here are the colors mean that those areas are flooded for that date. It has nothing to do with the intensity of that color. Each date we have one color. So everything that was inundated for that particular day, I colored with a specific color. So if you go here under layers, everything that was flooded, the total flood extent for the 21st of August is in green. The total flood extent and the other, so let me just, yeah. So the total flood extent that occurred on August 27th for this area is in yellow. And then the total flood extent on September 2nd is in orange. That's what it means. The color is the same color. There's no intensity difference here. Okay, the next question. Initially, how am I going to decide a threshold, like 1.25 in the script, without knowing? Depending on what parameters or threshold will be decided, or is that like applying and checking and updating? Absolutely, the threshold is applying and checking and updating. And it is trial and error. So I suggest you go and you try different thresholds, especially if you have validation data that you can then compare whether your threshold is identifying your inundated areas that you have where you have validation. That's the best thing. Another thing you can do is, remember I showed you how to click on a pixel and look at that pixel value. So one thing you can do, so let's go to the difference. So we know that the bright areas are areas where inundation occurred between, in this case, August 9th and August 21st. And so if we click on any pixel, and in this case, I'm clicking on this very bright pixel here, I'm going to get the value here in the inspector box. So that would be here. This is the value for that pixel I clicked. One thing you can do is you can actually draw a polygon over your bright areas to uh, calculate what is the average of your values within your bright areas, and maybe define a threshold based on that, or look at the histogram and then define a threshold based on that. But certainly defining the threshold is trial and error. All right, the next question. When doing a large-scale flood analysis, for example, an entire country, is connected pixel able to perform that fast enough or during such analysis? Or does the region of the study area need to be subdivided to match the maximum number of pixels allowed by Google Earth Engine? Yeah, that's a good question. Some of these things do time out because the domain is so large. So you're gonna have to see what works for you. And it might be that if it's too large of a region, it just won't compute that calculation. But yeah, I'm not sure exactly how it would work for this specific function connected pixel. The next question, number 7, how would you differentiate between inundation in urban areas and inundation in forest vegetated areas? Super great question. So remember I explained the backscatter mechanisms, and there's double bounce. So you have double bounce in inundated areas, and you have the exact same backscatter mechanism in urban areas. So since it's the same backscatter mechanism and these areas appear equally bright, it's not that we can differentiate like between them. So the best way to differentiate between them is to take a map or a shapefile of delineating urban areas, urban centers, and then mask those areas out. That's really the easiest. And okay, so one more thing to add is that inundation in urban areas, obviously in urban areas, you already have high backscatter without inundation. And then if you have some sort of inundation in urban areas, you might have additional high backscatter. So you just have to see what additional high backscatter areas between two different dates. So a pre-event in an urban area, a pre-event image, and then a post-event inundation image, and see which additional areas within your urban center have high backscatter, okay, to identify inundated urban areas. The next question, is there a way to set the upper threshold automatically so that the flood extent can be produced easily for any area of interest? Yeah, that's another good question. I mean, all of these things, obviously, it becomes, ultimately, we want to automate all of these things. So I think, yes, what you can do is you can maybe, as I mentioned, you create a geometry for these bright areas. So let's so you identify a couple of those, and then maybe you look at the histogram and you define different cutoffs, yeah, for these areas that are bright, and you run your algorithm, you apply the threshold, and you validate it with different values, with different threshold values, and then this is all in an automated way, and then you identify which threshold is the most accurate. So all of that can be automated. Okay, the next question. Can SAR be used to identify different types of water based on dissolved substances, say a muddy water, clear water? No, it can't, not directly. So optical is sensitive to the chemical properties of your land surface. With optical, you can see muddy water, you can detect different levels of chlorophyll, for example, things like that. Remember, SAR is sensitive to structure, roughness, and dielectric. So I said not directly, but maybe indirectly, you might be able to identify that your water has different characteristics given the roughness, the surface roughness of your water. And we'll see a little bit of that actually on the third session of this webinar series, where we're looking at detecting oil spills with SAR. So what happens when there's an oil spill? The surface roughness over the area that's covered with oil, or over the water that has oil on it, the surface roughness is different than the surface roughness of the water that doesn't have oil. And so that's how you identify these oil spills. And perhaps these waters that have different characteristics because of the sedimentation, they might have different surface roughness characteristics. But that might be a bit of a stretch. All right, so let's keep going. So the next question. Okay, question number 10. How can we generate layover and shadow masks using Google Earth Engine? Yeah, that's a really good question as well. Okay, so the images that you extract, so in the case of Sentinel-1, each image or each date has actually 3 images associated with it. And one is, there are 2 polarizations, and then there's the incidence angle. And what you can do is take the incidence angle and hold on, let me think this through. I'm sorry, I take that back. So what you want to do is you want to use a digital elevation model and basically mask out your areas of complex topography. So shadows, what you can do is take a DEM, create a mask in the areas where you have complex topography, and then look at the values within that area of complex topography, and look at the values, areas where your values are 0, for example, or not 0, are very, very low. So that means those are areas where there's shadow. And you can then maybe set a threshold and say, okay, well, within my area of complex topography, the pixel values that are less than -30, for example, mask them out. So that's how you would mask out shadow areas. And then a layover, you would have to use the digital elevation model and the incidence angle to identify areas of layover, kind of in the same way. The next question, what is the min-max value here and what is the last value in the array? Okay, so I did explain, the min-max. So let me go back and show you what happens when you play around with that min-max. Okay, so here we have an image. This is the one from August 21st. So let's go here into the cogwheel. And the min-max values are just to set the visualization range. So you can say, okay, let's set this to 30 and see what happens. It's how you stretch your pixel values in order to visualize them. All right, so it has nothing to do with changing the values or within your image. It's just purely for visualization purposes. What does the 0 mean at the end? That means that, again, this is for visualization purposes. So if you have a 0, that means your image is going to be added to the layers bar here. However, if you want to visualize your image, you have to click on it. If you set this to 1, it will automatically activate it when you run the code. Okay. So in this case, since I've set this to 1, my August 10th image, it will automatically be loaded, appear when I run the code. Okay, if I don't want it to load, I just go back and set that to 0 and run it. And then in order to load it, I need to click on it. All right. Question number 12, what does the dot multiply function do? So I use that function to calculate the area. So basically I counted the number of pixels that were inundated and I multiplied that by the pixel area, the pixel resolution. So that's the way I calculated the area, the extent of flooded area. Can we quantify uncertainties associated with the final flood extent map by using any statistical means? I'm not sure I fully understand that question. I think if you have some validation data, absolutely, then you can compare the areas that were classified as inundated and that were actually inundated based on your validation data. And then you can generate an accuracy, a percent accuracy assessment. Can we upload our own created land cover map created using Sentinel-2? Of course you can. So if you go to Google Earth Engine and you go to Assets and you click here on New, you can upload your own image. So you can upload actually a GeoTIFF image, or you can upload a shape file or CSV file. Okay, is it possible to derive flood depth from this flood extent map? No, it's not. So what we're looking at here is just inundation. And yeah, flood depth, that becomes a bit more complex. The response, the radar response, is sensitive to standing water above the soil surface. Whether it is standing water 1 centimeter above the soil surface or 10 meters above the soil surface, the radar response is the same. Is this code like an automation of the manual work that can be done in Snap software? That's a good question. I'm not familiar with uh, what you mean by the manual work that can be done in Snap software. I can tell you that with Snap, if you were to download these images, you would probably have to do the pre-processing. So you would have to do the radiometric correction, the terrain correction. But I'm sure you can go through these same steps through Snap. That there's no doubt about that. It's just facilitated here because you've got the entire database online and you can run these things online, and it saves you from downloading for radar images that are about 1.2 gigabyte each. Okay, question 17. Can we go lower than 10 meters in Sentinel-1? It's another really good question. Not with the GRD. These are ground range projected data sets. They are at 10 meters. In fact, it's not actually 10 meters what we're generating in reality. And the reason for that is because we're applying a speckle filter, right? So let's just, and so that speckle filter is actually reducing your spatial resolution, even though it's still gridded at 10 meters after applying the speckle filter. The actual resolution has been reduced. So let me just show you what that means. So here we've got the August 9th, the original one. And on top of that, I've got the speckle filtered image. I'm just going to turn some of these layers off so that they don't distract. Okay, so that's the original one. So that's the pre-filtered native 10-meter resolution. And then this is the filtered. So you see that it becomes a little bit blurry. All right, question 18. Sentinel-1 C-band on Google Earth Engine has not been really helpful in detecting floods in forests. Is there a way to process the SAR-band C-band data to improve on the detection of flooded forests, or some post-processing methods? Yeah, that's another great question. It's not a matter of processing the data, it's really the physics of the data. So C-band, as mentioned, that has a wavelength of around 5-6 centimeters. And so by nature of the signal, you're not going to be able to penetrate through dense forests. All right. You will need L-band to penetrate through dense forests. Now, in some cases, some forests have a lot of gaps in them, and you might be able to penetrate and detect flooded vegetation, for example. But it's really a matter of the characteristics of the signal that allow you to detect these type of things. It's at this point is not improving on the processing methods. Question 19, do you have any suggestion to access validated criteria for selecting thresholds? It's another really good question. I don't have any, other than, as I mentioned, I think one of the things you can do is really take a look at the polygons, take a look at the histograms, or calculate the mean, and then that gives you a sense for the values of the areas that you want to mask as flooded. And yeah, that might be a better way to guide your selection of a threshold. Which constraints do you see on applying SAR products in detecting flood areas in urban regions? Yeah, it's tough to apply SAR for detecting flooding in urban regions, and that's because of what I mentioned. You already have double bounce in urban areas, and so flooding will cause more double bounce. Also, you might have specular scattering in urban regions that have been flooded. I mean, you have a lot of parks and things like that, open areas where you have standing water. So it just becomes a little more difficult. Urban areas tend to be smaller in extent. So I think what you would have to do is set an upper threshold and a lower threshold. Question 21, what is the impact of depolarization on scattering from objects? I'm not sure I fully understand this question, but as mentioned before, your signal tends to depolarize whenever you have a volume scattering, basically, and whether that volume is vegetation, whether that volume is a soil volume, snow volume. Question 22, can we use higher resolution land cover maps such as ESA world cover? Yeah, of course, to remove misclassified pixels in areas where there is permanent open water. Yes, absolutely. In this case, I use this one, but you know what, that ESA world cover map is on Google Earth Engine, and I can show you again very quickly. So all you do is, let's see. ESA world cover. And instead of using that data set that I used, you call the ESA world cover map using this command. And that's it. Okay. Okay, thank you for your presentation. For line 16 of the script, why did you include the 999 when you had to put it on the list? Yeah, that's just for, it wasn't needed here. That's a good point. So basically I created a list with just 8 images, but if your list is very long, well, that it has many, many images, then you want to specify that, hey, this is a long list, make space for it. Otherwise, it's not going to work. In question 3, you explain why using VV instead of VH to detect inundated crops, but shouldn't HH be equally good as VV for that? Yes, I explained VV because that's what Sentinel-1 has. It's VV and VH. So between VV and VH from Sentinel-1, VV is the better polarization, but HH is actually even better. I have a question for Sentinel-2 on Google Earth Engine. Is it possible to use a Sentinel-2 to map the flooded area? Is the image in dB or DN? What calibration has been done for Sentinel-2 datasets? Yeah, those are all good questions. You can use optical. That's beyond the scope of this. I mean, the idea here is to show you how to use radar to map inundation. It's particularly useful because usually areas that are inundated are cloud covered. So if you want to look at say almost real time, extent of inundation, these areas tend to be cloud covered and you want to use radar images. The radar images are in dB, and what calibration has been done for Sentinel-2 datasets, you will have to take a look. But I can tell you that for the Sentinel-1, I showed that at the beginning, that the data are basically analysis ready. They've been radiometrically corrected, terrain corrected, and all that needed to be done was to apply a speckle filter. But for Sentinel-2, you'll have to take a look. There's Sentinel-2 top of atmosphere. There's surface reflectance. So there are different data sets associated with Sentinel-2. Question 26, will the values of extent of flooding vary in open waters in different bands like C and L? Yes, they might vary. I mean, specular scattering is always going to be very low, but it will vary. It's always good to click on open water bodies to have an idea of what the values are. And it may vary if you have some sort of roughness on your open water body due to wind or maybe short floating vegetation. Can I determine present and past surface melt on an ice sheet? Which polarization will be better, HH or HV? Yeah, that's a whole other topic on its own. And yes, you can determine surface melt. There is a large change in the dielectric between frozen and when things are frozen and when you have liquid water. So yes, you can certainly take a look at these sort of issues with radar. Question 28, does the signal response differ if the flood consists of a lot of soil, sand, debris? For example, flood in mountainous volcanic areas. No, because as long as that surface is a specular scatter, it's not gonna differ. It's not, yeah. 29, can trees and canopy lead to underestimation of flooded areas? So when you have inundated vegetation, the flood signal is different. So when you have open water, it's dark, it's specular scattering, inundated vegetation, then it is very bright. Okay, it's double bound. So it's two different scattering mechanisms that you need to look for. And in that case, you would have to set an upper threshold and a lower threshold. How can we use full polarimetric data for flood inundation mapping? Yeah, it becomes much easier to detect flood inundation with fully polarimetric data. However, the challenge there is obtaining fully polarimetric data. But there you can do decompositions and look at, for example, areas where double bounce dominates, and then identify those areas or classify those areas as flooded areas. Okay, so that looks like it. And we're past the time. I'm sorry I went past. I got overexcited here answering everyone's questions. I'd like to thank everyone, all of the participants, your great questions, all of your enthusiasm. Please stay tuned. We will be posting this Q&A doc online in a couple of days. We're cleaning it up. We'll clean it up, put it on. We will be posting the recording. The PDF presentation is already there. Let me know if you have any questions. Stay tuned. We have two excellent presentations. Tomorrow, Thursday, Dr. Eric Fielding presenting on landslide movements, and then next Thursday, October 27th, Dr. Malene Johansson will be presenting on the use of SAR for detecting oil spill and oil spill extent and motion. So don't miss those. Thanks, everyone. Wishing you all a great day and a big shout out to the ARSET team for their amazing job in putting all of this together. Bye bye, everyone.